We got people. Hey, we got people. All right, lads and ladies, welcome back to Calc 2. Today is an exciting day. But before I get into the exciting stuff, I want to talk about some boring stuff, some bookkeeping stuff. It is the case that we're a little bit short on time here. Always seems to be the case, but we just can't sacrifice a good treatment of power series. There's no replacement for this shit down the road. So I'm going to talk to you a little bit about how we're going to map out the remainder of the course. I got a few emails with specific requests. I want to address those to the group rather than individually. So my camera starts listening to me. So it's working, but the Zoom is frozen. I'm going to power cycle this real quick. So one of the requests I got was to do exam 3 as a take-home test. This is something I've done in the past. I'm not averse to it, but it will mean it's a harder test. So it would give us a little bit more time to spend on some of the materials that I want to talk about. So for that reason, it is tempting. No, not that. God damn it. Let's connect. There we go. Here we go. All right.
What do you mean by take-home test? I'm sorry.
Yeah, I'll explain. So let's get this out of the way. This is MAC2312, section 004. It's a lecture. And today is the 15th of April, 2021. All right, so today, definitely more power series. Discussion of exam 3. That's about it. Right, so kind of here are our options, and none of them are perfect, but this is just the way she goes. Today we're going to talk about power series. Today we're going to finish power series, meaning we're going to, I'll play a little bit more with 11.9, but then we're going to move on to 11.10. We're going to cover all of 11.10 today. That leaves just next Tuesday and next Thursday for those last few topics, the kind of disparate topics, which are like polar coordinates, parametric equations, and some application stuff like surface areas. Ideally, that would be, I would have a week for those things. That's usually what I build into the schedule, is a full week to address those topics. But because we would need one of those days for the test, we don't really have a full week's worth of time. So what I'm thinking is that we could do the take-home exam 3. And what that means is that exam 3, rather than being on Canvas, this would be kind of like a worksheet. With an honor pledge, saying, I swear to my grandmother and my dog from childhood and all the things on this world that I love that I really didn't Google any of this shit or talk to someone in class. And it would be due on the day of the final. So that's what I'm leaning towards. This would be a take-home test. These problems really aren't the sort that you can throw into Symbolab or something like that, with some exceptions. Most of them are going to be, power series things, things like that require geometry sketching, that sort of stuff. So I'll make very clear what you would be allowed to do and what you wouldn't be allowed to do on this.
When is the date of the final, by the way?
I'm sorry, Ethan, what was that?
When is the date of the final, by the way?
So your guys' final, I've got your syllabus up here, and then we do want, yeah, we can vote on this, that's fine. I'd be happy to do that. So your guys' final, here you are, is the 27th, and that's one of the things, that's next Tuesday, or not next Tuesday, but the Tuesday after next. So if we were to do this, like, well, let me lay out the other plan, right? So one of the options is to do this as a take-home test, which is like a worksheet. And this would be due on the day of the final. At the start of the final. That's one option. The other option is to do exam 3 in class on Thursday. But I would pre-record an extra lecture for you guys to watch over the weekend. So we can either like use next Thursday as our extra day for lecture that we need before exam 3 and then do it as a take home, or I can shove an extra day of lecture into the weekend instead of using Thursday. But we're going to need one more day, basically. I do not want to try and squeeze parametric equations and polar coordinates down into one day. Each of those topics is a one-day thing. So really, I need 2 days of lecture here before you'll be ready for the exam properly. So those are kind of our options, right? We either do exam 3 as a take-home that I would give you on the last day of class, which I think for you guys is the 22nd, and then would be due on the 27th at the start of the final. Or I can add a pre-recorded, right, non-interactive, or we could do it interactive if you wanted and just record it and publish it on like a Saturday, extra lecture where we can spend that one extra day talking about the polar coordinate stuff. And then have the lecture in class on Thursday. The date there would be 4/22/21, I believe, next Thursday.
Would the test be made considerably harder if it was given as a worksheet?
Well, this is the thing. So if we're going to do it as a take-home test, I need to make it ungoogleable, right? That's the thing. Because no matter what I put in that honors pledge, like I'll hunt you down and kill your cat,
Yeah.
someone's going to try to Google something. I've just been doing this too long to know that.
It's understandable.
Would be considerably harder. It's not going to be easier. I mean, there definitely ain't going to be problems out of the book, right? So it's going to be stuff that would be a little bit more conceptually focused, stuff where I give you a little bit of information and you have to fill in the rest. I think this would be a much more concept and graphing and blah 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 test. This would be more like a regular test, but with this caveat that one of the lecture days would be lost because we have to spend that day on the test. So you would need to either watch a pre-recorded lecture or come to a lecture on a non-normal lecture day, which I feel is a little bit unfair, right? Because I know you guys have live schedules, things outside of this. I can't say we've got class on Saturday, but I could record a lecture and say you can watch this anywhere between, today and next Thursday. So
That is a hard decision.
yeah, the request was that we do a poll. I'll give you guys some time to think about this. All right. So remind me at the end of class, we'll do a poll. So you got some
I have
time.
a question about this.
Yeah.
The honor pledge work take-home test. Would you still be grading it and reviewing it as if it were a test?
Yep.
Okay, because the biggest thing. I don't really care about the test. I care about the final exam in this case because we're cutting it close, to be honest.
Yep. Yeah, it is. It's tight. It's really tight. Spring semester here is like 2 weeks shorter than UF's fall. So it's really difficult to have a class that's mandated by UF's fall curricula squeezed into our spring. It is tight. The test would be graded according to the same ethos that I always grade tests. I'd build a rubric, the true false are 2, multiple choice are 3, and free response are 5, or double that, to scale to 100 because we need 100 points. So true false would be 4, multiple would be 6, and free response 10. So it'll be the same length. It'll be the same grading ethos, but the content of the test itself, if we do the take home, is going to be more concept oriented. The content of the test, if we do it in class, would be like a regular test, i.e. more calculation oriented.
What do you mean by more concept oriented? Like, how would that manifest?
Well, so like having you sketch pictures, having you explain theorems, giving you some hypotheses and asking you what would be the consequence of those things. Like if I have a power series centered at 5 that converges when you plug in x equals 6, would it necessarily converge when you plug in x equals 4? That kind of shit. Asking you to sketch an interval of convergence with a little bit of information. Maybe I give you the limit L from the ratio test for this series and I say sketch the IOC, rather than just giving you the series and saying find the IOC. Because if I just give you the series and say find the IOC, it's real easy to type that in somewhere and get the answer. But that's what I mean by more concept focused.
Would it be like this on the final exam as well?
No, the final is going to be a straight regular proctored exam. That is inflexible. I'm unwilling to compromise.
No, I mean in terms of if we do the as exam 3 as more concept oriented, will the more concept oriented problems be transferred to the final exam as well?
The decision here has no bearing on the final. So the final will be what the final will be regardless of what we do here. There will be some concept oriented stuff on the final, like there is some concept oriented stuff on all tests. But the balance of calculation versus concept on the final is not going to be affected by what we choose to do here. Does that make sense?
Yes, thank you.
Okay, cool. Alexander, yes, a Thursday, a week from today. Yes. So if we do the in-class test, that would be a week from today. We would be doing it. The main content of that test is going to be power series, but there are 2 other big things that we need to talk about. I guess there's a third option here, really. We could do the in-test class on Thursday, and I could omit the chapter 10 stuff and just put that on the final. So if we want a third option here, so in class on Thursday, but I pre-record an extra lecture and the in-class test covers everything, i.e. power series, parametric equations, polar coordinates. The last option here, and this is something that professors at Santa Fe do, we could do the in-class on Thursday, and with extra lecture. But the chapter 10 material is just on the final, not on exam 3. I advise against this third option. I advise against this third option precisely because it would mean test 3 is all power series. And the truth is, the parametric equations and polar coordinate shit is easy. The reason I split it like this with power series together with parametric and polar is because the parametric and polar stuff kind of softens the very difficult power series stuff. So this third thing is an option. I do know 1 or 2 professors who do it this way. They take those last 2 kind of easy topics. They don't put them on exam 3. They just put them on the final. That is one way we could do this. Just be aware that means exam 3 is all power series, which is all tough. So we'll have a little poll at the end of class. You guys can decide which of these 3 options we want. Josh asks, if I have a final at the same time for another class, what should we do? So first, that shouldn't happen, right? Like triple check and make sure that that's the case, that you actually have a conflict with your final exams. If you do have a conflict with final exams, the only ones I'm aware of are like usually 1105 and BSc 2010 sometimes conflict. I know that the math department here has an arrangement with the natural science department that says math finals take precedence over nat sci finals. So the nat sci people are forced to reschedule. But I've never seen that with MAC 2312. So if you're running into that, let me know via email what the conflict is, the professor and the class that conflicts, and I will reach out to that other professor and we'll figure something out. All right, bueno. Okay, so be thinking about those 3 options: take-home exam that covers everything, in-class exam that covers everything with an extra lecture inserted over the weekend, or in-class exam that doesn't cover everything would just be power series, moving those extra topics from the extra lecture just onto the final. That's going to make exam 3 brutal in the sense that it's harder stuff. It's all power series, but it would also mean you have less to study for just for exam 3. So you could prep up to Thursday just for exam 3 and then prep between Thursday and the final for those extra materials and whatever else you wanted to study for the final. All right, that's enough rambling about this stuff. Let's return to power series. So today we finished power series. Oh no, this is pen dying. Let's load it back. So one of these is still right. Yeah, okay. Last time we saw how to integrate and differentiate power series. We did that primarily in order to come up with power series for different functions. Before we dive back into the material, I want to remind you some crucial power series that we will be using as starting points moving forward. So I say recall 1 over 1 minus some shit can be rewritten as sigma n from 0 to infinity, that shit to the n. I'll write all of these in terms of the variable u. And the idea is, of course, that we're going to plug different things in for you to get other power series. Other ones that we came up with last time were the inverse tangent. Last time we wrote it as inverse tangent of x. I'll write it as inverse tangent of u. Here with the intent again that we can plug different things in for u, and we don't have to start all the way over when we're after a power series. So if you want the power series for arctan of x cubed, you would just plug in x cubed for u here. This is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times u to the 2n plus 1. We cooked up a few others, but none are super important. There's one more that I'm going to cook up for you here. I'll just show it to you now so you can have it in your, well, let's derive it. Plus one more important guy. So this will be our first kind of working example for today. Maybe leave some space here in your notes for this one more. You can come back and that way you have them all in one place. Example. Let's see if we can find a power series. For f of x equals the natural log of 1 plus x. So this one is kind of similar to the arctan one, in that I know how to get ln of 1 plus x as the integral of something. We know that the ln of 1 plus x plus a constant is equal to the integral of 1 over 1 plus x dx, right? This integral is a very straightforward little u sub problem. If you were to sub, I'll say z sub so we don't confuse it with the u's above. If you sub z equals 1 plus x, then dz is dx. This becomes the integral of 1 over z dz. And you would get the natural log of the absolute value of 1 plus x there. It turns out I don't really give a shit about the absolute values here because the radius of convergence is going to be small enough that the inside of the log would never be negative. So this is a fact. Using the geometric series trick, I can write this as the integral of 1 over 1 minus negative x. And then because we know that 1 over 1 minus u is sigma n from 0 to infinity, u to the n, I can replace the integrand down here, 1 over 1 minus negative x, by sigma n from 0 to infinity, negative x to the n. That's exactly what we're going to do. This becomes sigma n from 0 to infinity negative x to the n dx. And I said it in the other lecture, but I want to say it again here just to emphasize, before you integrate or differentiate your power series, you need to simplify the inside. I need to write this in the standard form for a power series, like Cn times x minus a to the n. And what I mean by simplify here is exactly that. I need to rewrite this negative x to the n as negative 1 to the n times x to the n dx, because the integral is only going to affect the x, right? Stuff with n's, including the sigma, are constant with respect to the integral. So now, following the integration formula from last time, I've already got my plus c on the other side. I'm not going to write it again. I've written it here. The integral of sigma n from 0 to infinity, negative 1 to the n times x to the n dx is sigma n from 0 to infinity, negative 1 to the n times 1 over n plus 1, n plus 1, x to the n plus 1. Add 1 to the power, divide by the new power. It's as though you can ignore all the series stuff, right? If you ignore all of this and you just integrate x to the n, you get 1 over n plus 1 times x to the n plus 1. Normally, I would write a big plus c out front here, but I've already written the plus c over here. So what we've got here is that the natural log of 1 plus x plus some constant is equal to sigma n from 0 to infinity, negative 1 to the n times 1 over n plus 1, x to the n plus 1. And like we did for the inverse tangent series, we're going to need to solve for c, right? I don't want to know, or I want to know exactly what is the power series for ln of 1 plus x. I'm not okay with just knowing it modulo an additive constant. The trick for that is to write out the power series long form and plug in the center, x equals 0. So this is equivalent to ln of 1 plus x plus c equals, and we write out the terms here. So when n is 0, we have 1 times x. When n is 1, we have negative 1 times 1/2 times x squared. So that's minus 1/2 x squared. And then, and then we have plus 1/3 x cubed minus 1/4 x to the 4, and so on. So these are the first few terms of that power series. This is that power series written out in the ... notation. And if I evaluate this at x equals 0, I will get the natural log of 1 plus a constant is equal to 0 minus 1/2 times 0 squared plus 1/3 times 0 cubed minus 1/4 times 0 to the 4, and so on. So every term over here is 0. The natural log of 1 is 0. So this is just saying c equals 0. Because remember, the ln of 1 is 0. Thus, we arrive at the ln of 1 plus x equals sigma n from 0 to infinity. I'll write this as negative 1 to the n over n plus 1 times x to the n plus 1. So this is my power series for the natural log of 1 plus x. You could rewrite it in terms of the variable u. And that gives you your last kind of crucial power series from section 11.9 that we need to hold on to. We should be concerned about the interval of convergence here. And the geometric series that we started with at this step, this is kosher as long as the absolute value of negative x is strictly less than 1. It's the geometric series trick. This is good as long as abs negative x is strictly less than 1, which is equivalent to saying abs x is less than 1, which is equivalent to saying negative 1 is less than x is less than 1. So the IOC for this series, not the final series, but the IOC for the series that we integrate is the open interval from -1 to 1. That's the IOC here. And now I want you guys to tell me what happens when you integrate a power series. What effect can that have to the interval of convergence? There was some discussion of this in a pre-recorded lecture.
If I remember correctly, the interval of convergence can't change, but you can find one or more of the endpoints.
Yeah, so that you're correct, but I want to be very careful about the language. So the radius of convergence cannot change, right? The radius has to stay the same. And since the center is 0 and the radius of the series with which we began is 1, my new IOC still has to have the endpoints -1 to 1, right? It's still, so the original series had this as its IOC. And then the crucial thing is the last part of what Ethan said there is that you can pick up an endpoint when you integrate. So what are the possible IOCs here? It could be the same. Maybe we don't pick up any endpoints, or we could pick up the left endpoint and not the right, meaning it could be left closed, right open, or it could be totally closed. It could be like the arctan series where you pick up both endpoints when you integrate. Imagine I plug 1 into this series. I plug in 1 for x. What's the output? Well, if you plug in 1 for x, this piece just becomes 1, right? So you're just left with sigma n from 0 to infinity, -1 to the n over n plus 1. What is that? That's a series we know. It's an alternating series. It's a particular alternating series. It's the alternating harmonic series. It's just index shifted down. So this series, when you plug in 1 for x, you get a convergent series. What about when you plug in -1 for x? This would be -1 to the n plus 1 times -1 to the n, which is -1 to the 2n plus 1, which is always -1. So then you would get the negative of the harmonic series without any alternating behavior. So that would diverge. So the IOC of this series is -1 to 1, like this. The radius is still 1. So that's the convergence information you need to remember along with this series. This is also way back when we were first talking about series and we played with some partial sums. I said this series converges to the natural log of 2. That's where this comes from. If you plug in 1 here, you get the alternating harmonic series on the right, but on the left, you get the natural log of 2. That's how I know that the natural log of 2 is the sum of the alternating harmonic series. All right, questions on this derivation? Okay, so then to your list, here, we're going to add this guy. The natural log of 1 plus u is sigma n from 0 to infinity, -1 to the n over n plus 1 times u to the n plus 1. And this is your list of 3 crucial power series that you have to remember from section 11.9. And the idea is you can use these as a starting point to find other series. So I'll work one or two little problems here, and then we're going to move on. The intervals of convergence for each of these. This one is closed on both sides. This one was open on the left and closed on the right. The middle series is a great tool for getting a series representation of pi. You want to know what's the millionth digit of pi? You plug in 1 to this series, that'll give you pi over 4. So multiply that by 4, and then use your estimation theorem for alternating series to get whatever level of accuracy you want. It's a really nice tool, and it's what Newton and Leibniz would have used to approximate pi back in the day. Since we've developed some faster converging series like this, but it's very nice. All right, so what do we do with this? Well, there's some problems we can solve now that we couldn't solve before. So I could ask now to integrate arctan x over x. This is not something we could have done before. None of the methods we learned at the beginning of the semester, indeed no elementary methods at all, exist which will allow you to evaluate this integral. But if we can rewrite the inside as a power series, then we can integrate that as a series. Your answer is going to be a power series, but that's okay. Oftentimes, power series are the easiest way to evaluate transcendental functions anyway. What you'll find is if you're going into any sort of engineering or any sort of physics-y or hard science thing, 9 times out of 10, when you want to work with a function, the very first thing you're going to do is expand it as a power series. So to solve this problem, we begin by saying, recall that the inverse tangent of x can be written as sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. Which means that the inverse tangent of x over x, which is 1 over x times the inverse tangent of x, can be written as 1 over x times that power series. And the nice thing about this is that this 1 over x doesn't have any n's in it. So it can come inside the series. With respect to the summation operator, the 1 over x term is constant. Summation operator only cares about n's. This doesn't have any n's in it. So this can come inside. Giving us sigma n from 0 to infinity. We'll move it right past all this other stuff. We have -1 to the n over 2n plus 1 times 1 over x times x to the 2n plus 1. And these two guys can interact. We're dividing x to the 2n plus 1 by x. So you subtract the powers, right? This, and we've talked about this algebra stuff a few times because this sort of thing showed up back with ratio test work. That gives me sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n. Right, like x cubed over x is x squared. X to the 5 over x is x to the 4. The power comes down by 1. So here is a power series for the inverse tangent of x over x. And that's what I meant when I said we're going to be using this as a starting point. Right? I didn't want to rediscover this. I want to just begin with this. And then I can build my integrand out of that. So relatively quickly, I get a power series for arctan x over x. Therefore, the integral of arctan x over x dx is the integral of sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n dx. I know this stuff looks scary. It's great for terrifying freshmen. You want to scare the shit out of your friend who's thinking about studying engineering, just show them a little bit of this. But it's really not that bad. Remember, the integral doesn't care about these things. All the integral sees is x to the 2n dx. It's a power function. You're integrating a power function. It's like a polynomial. So you integrate it like you would integrate a polynomial. You add 1 to the power and you divide by the new power. Here, since I didn't have a plus c already like we did in those other problems, I write my plus c at this step because I'm doing the integral. Then we have sigma n from 0 to infinity, -1 to the n over 2n plus 1 times. Here I add 1 to the power and I divide by that new power. So it's going to be 1 over 2n plus 1 times x to the 2n plus 1. And that's it, you're done. You can simplify this just a tiny bit if you want. I can write this as -1 to the n over quantity 2n plus 1 squared times x to the 2n plus 1, but that's as much as we could possibly hope to do. This is an indefinite integral. The answer should have a plus c. There's no need to solve for c here. Remember, indefinite integrals, you always have a plus c. So this is an antiderivative for arctan x over x. That's hot shit. Right? Antiderivative for this function, incredibly hard to find, but here it is. It's just a power series. That's just the nicest way to write it. There is no nicer way to write that function, but this works as long as you stay within the interval of convergence. Now the IOC for arctangent was the closed interval -1 to 1. You might ask, does dividing by x, does bringing this 1 over x into the series change the IOC? The answer here is no, but in general, you might be nervous So it would not be unwise to freshly run the ratio test here, or at least examine what the IOC should be. I'll tell you it's the same. The IOC here is still the closed interval from -1 to 1. In other words, multiplying or dividing by x in a power series won't change the IOC. And then integration could only add endpoints. But since this guy already had both of his endpoints in the IOC, no change can take place. So even without the calculation, if we think critically, we know that the IOC still has to be -1 to 1, closed on both sides. This sort of problem is a classic, right? This is like the goal. The reason we've been doing all this shit with series and sequences from the end of spring break till now is to get you to a place where you can do this, where you can solve integrals that were previously unsolvable by expressing the integrand as a power series. So I'd like to look at least one more before we jump into 1110. I think I gave you this one on your homework, so I don't want to do the other integral in your homework right now. I want to grab something that's not there. Let's see what I've got. We could do 3132. Definite integrals are fun, but they require a little bit more futzing about. Let's look at number 27. This is about the level we're working on right now. X squared times the natural log of 1 plus x. There's questions on this. Okay. So again, this is not an integral I know how to do otherwise. Although we might be able to attack it a few different ways. The problem is telling us to do it as a power series. So we need to rewrite this thing as a power series. And the trick is that I know how to rewrite this part as a power series. So I know a power series for ln of 1 plus x. I can use that to get a power series for x squared times ln of 1 plus x. We recall that the natural log of 1 plus x is sigma n from 0 to infinity, -1 to the n over n plus 1 times x to the n plus 1. Which implies that x squared times the ln of 1 plus x is x squared times that power series. And just like the 1 over x could come into the series last time, the x squared can come into the series this time. So this will be sigma n from 0 to infinity, -1 to the n over n plus 1 times x squared times x to the n plus 1. And again, the algebra here is easy. X squared times x to the n plus 1 is x to the n plus 3. We add the powers. So here's your power series for x squared times the natural log of 1 plus x. It's this. Again, we should ask, has the IOC changed? And again, the answer is no. So the IOC here was left open, right closed, -1 to 1. And the IOC here is still that. Therefore, the integral of x squared times the natural log of 1 plus x dx is the integral of this series, sigma n from 0 to infinity, -1 to the n over n plus 1 times x to the n plus 3 dx. Remember, the n's are in no way related to the integral. The integral doesn't care about the n's, it only cares about the x's. It's an indefinite integral, so we'll get a plus c. We like to write the c out front rather than behind, so it's clear that the c is not inside the series, but outside. And then you just integrate the x's. You integrate like a polynomial. So it's -1 to the n over n plus 1. If I add 1 to n plus 3, I get n plus 4. So this is going to be 1 over n plus 4 times x to the n plus 4. It's really not that bad. Remember, we're just integrating this piece. So you add 1 to the power, n plus 3 becomes n plus 4, and you divide by the power. If it feels more natural to write this as x to the n plus 4 over n plus 4, you can do that. I'm writing it like this because it's just nice to group the n stuff and the x stuff. The IOC here is a little bit interesting. So problem done, right? This is the end of the problem. The IOC here is a little bit interesting. We do pick up the left endpoint. If you plug in -1, this is a convergent series because the bottom is quadratic. So it's like an alternating 1 over n squared. And that'll converge regardless of whether it alternates or not. So the IOC here is closed on the left, closed on the right. So this time when we integrate, we picked up an endpoint. It's very nice. Okay, there's lots of other problems like this. We could take arctan and substitute whatever power of x you wanted inside, and then integrate that by integrating it as a series. The natural log of 1 plus your favorite thing, natural log of 1 plus your mom, we could integrate that. Whatever we want, we can do now, as long as we can write it as a series. So the game moving forwards is to find more power series. And I kind of previewed the other important ones in the past, e to the x, sine x, cos x. Those are a big deal. We really want those guys. So I'm going to begin now section 11.10, which is the last section on power series. Yay! But it does involve some tricky biscuit stuff.
Could you quickly re-explain how the interval of convergence changes from open to closed?
So what happens, this is actually pretty fascinating. If you think about it in this context, the series we began with, if you plug in 1, you get -1 to the n over n plus 1. That will converge as an alternating series. If you plug in -1, you would get -1 to the n times -1 to the n plus 3. That's -1 to the 2n plus 3, which is not necessarily even nor odd all the time. So it's not necessarily an alternating series. But the big thing is that the denominator here is linear, whereas the denominator here is quadratic. So when we integrate, we gave more shit to the denominator. We throw another factor of n downstairs, really a factor of n plus 4. So if you wanted to verify this, the way to verify it is just to plug in the endpoints, just to test. And you'll see that this series converges absolutely at both endpoints, at -1 and at +1, because the denominator would be like n squared. So I don't really give a shit what's going on up here because it's bounded. But in greater generality, the endpoint stuff, here, first let's just say x equals 1. I'm going to ignore the c here. We have sigma n from 0 to infinity, -1 to the n over n plus 1 times n plus 4. If you'll excuse me being a little bit sloppy, right? The 1 to the n plus 4 is gone because it's just 1. This is a lot like sigma n from 0 to infinity, -1 to the n over n plus 1 squared.
And forgive me if this is a dumb question, but how did we find out the IOC was -1 to 1, just given that equation?
Oh, well, so up here we started with a series whose IOC was open, left, right, close, -1 to 1.
Oh, we're just supposed to know that off the bat, or?
Right. That's so this
Okay.
this is kind of our starting point for the whole problem.
Yeah, all right.
So I knew that my endpoints were -1 and 1. I know that my center is 0. And then the observation that we pick up the left endpoint, that's not obvious. But it's what I'm trying to explain now. So this, again, you could say is kind of like, I mean, it's actually straight up equal to sigma n from 1 to infinity, -1 to the n plus 1 over n squared. Yeah, this one isn't even a shaky. This is just an actually equals. And you know that this guy converges. You could say he converges absolutely. You take absolute values inside and you get a convergent P series, or you could just say converges by AST, or you could say converges absolutely as a P series, because when you take absolute values in here, you get a P series. I'm definitely not being precise here, right? This shaky equal sign, this is not like rock solid logic. I'm just trying to convince you rather than prove rigorously here, because we're kind of done with our discussion on convergence. It's more about finding power series right now. If I plug in -1, then I'll have -1 to the n over n plus 1 times n plus 4 times -1 to the n plus 4, which is sigma n from 0 to infinity, -1 to the 2n plus 4 over n plus 1 times n plus 4. And since 2n plus 4 is always even, this is sigma n equals 0 to infinity, 1 over n plus 1 times n plus 4. And this could be shown to converge by direct comparison. The direct comparison test with sigma 1 over n squared. Again, the big idea is that the denominator is quadratic and the top is constant. So just like the argument here, the top is constant or bounded and the bottom is quadratic, means that you can kind of think of our series, bounded top, quadratic bottom, as being a lot like a P series with P equals 2. In this case, it alternates. In this case, it doesn't. But the inequality here would work nicely, right? N plus 1 times n plus 4 is bigger than n squared. So its reciprocal is smaller than 1 over n squared. So you could direct compare this series to this series. Making sense?
Yeah, thank you.
Yeah, I know it's quite a lot. It's not, we're at a place now where we're deep enough that a little bit of hand waving kind of becomes necessary. If you want to be 100% rigorous at each of these points, then it's very, very time consuming. So this is why we focus so hard on building intuition over chapter 11. All right. These are the sort of problems you're seeing at the end of the 11.9 homework, where you're asked to evaluate an indefinite integral as a power series. And these are some of the most important problems, not just in mathematics, but in physics as well. So please put some love into these. I promise they'll show up on the test. But the other thing we need to talk about today is section 11.10 on Taylor and Maclaurin series, which are still just power series. But when we think of them as Taylor series or Maclaurin series, we're able to get a formula for the coefficients without any geometric series trick along the way. So this is a section all about cooking up power series without using the geometric series trick. First, a Taylor series is just a power series. And a Maclaurin series is a power series centered at 0. So most of the series that we've been playing with are Maclaurin series, right? Pretty much all of the power series that we fucked with over the last couple lectures were centered at 0. You could call them power series, you could call them Maclaurin series, you could call them Taylor series. The big deal is that this man named Taylor found a formula for the CNs in terms of the derivatives of the function you're trying to expand. So most of the time when people refer to power series, you'll hear them call them Taylor series. That's the most common name. But it's just another name for a power series. And when you're talking about the specific case where the center is 0, you may hear them referred to as Maclaurin series. The big result is here. I'm just going to show it to you. Theorem. If f of x can be written as a power series, and I'll tell you what the conditions are for that. Centered at A, i.e. f of x equals sigma n from 0 to infinity Cn times x minus a to the n. Then the Cn's, the coefficients, the n stuff that's always in front of the x stuff in your power series, actually follow this really crazy formula. Where Fn at A is the nth derivative of f of x evaluated at x equals A. That's it. Now this I think kind of looks like magic the first few times you see it. There are other ways of stating this. Oftentimes you'll see people just say, alternate phrasing. If f of x has a power series centered at A, then that series is of the form, or that series just straight up is, f of x equals sigma n from 0 to infinity. They just plug in fn of a over n factorial times x minus a to the n. Again, where fn of a is the nth derivative of f evaluated at x equals a. And it turns out that the condition for f to have a power series is precisely the condition that you would need for this formula to be applicable. Since the formula for the CNs here, the formula for these coefficients involve the nth derivative of f evaluated at a, in order for this thing to make sense, f has to have derivatives, has to be differentiable. Not just once, that would just give you C1. Not just twice, that would just give you C2. Not just 3 or 4 times. F has to be differentiable infinitely many times. In other words, the derivative of f at A needs to exist for all derivatives, first, second, third, fourth, fifth, infinitely differentiable. Functions like these are sometimes called C infinity functions. That's actually a slightly higher restriction. To be C infinity means you have continuous derivatives of all order. Here we don't require the derivatives to necessarily be continuous, they just have to exist. I'll let you think about how it's possible those things aren't the same. That's a fairly subtle question. I would like to give you some idea of why this theorem is true, because it is so earth-shattering and working with it is so important. A Maclaurin series, remember, is just a case where a is equal to 0. So instead of x minus 2 to the n or whatever, you just have x to the n. So I'm going to offer the proof when a is equal to 0, just because it makes everything look a little bit nicer. So proof in the case where a is equal to 0. We're going to assume f of x has a power series expansion centered at 0, sigma n from 0 to infinity, cn times x to the n, and show that cn is indeed the nth derivative of f evaluated at a over n factorial. And the way you do this is kind of the only way that makes sense. You write this out long form and you differentiate, then plug in the center, differentiate, then plug in the center. Here, sorry, a is 0, right? So this should be fn of 0 over n factorial. No, I haven't fed him yet this morning, I think. All right. So we're assuming that f of x can be rewritten as this power series. If I write this power series out in long form, what does that look like? Well, when n is 0, I get c0 times x to the 0. When n is 1, I get c1x plus. When n is 2, I get c2x squared. I'm going to write out a bunch of these. c2x cubed My Calc 2 professor always made the horrible joke that C4 was the dangerous coefficient, like the explosive C4. I'm so sorry, but I just can't help it. C4x to the 4 plus C5x to the 5 plus C6x to the 6. This should be enough for us to get a feel. And remember, these C's, these are just numbers. They're constants. They're the coefficients. So like for the natural log series, C0 was 0, C1 was 1, C2 was negative 1/2, C3 was positive 1/3, and so on. This means that f primed of x should be what? Well, I differentiate each of these motherfuckers. I differentiate it like a polynomial. C0 is a constant. Its derivative is 0. The derivative of C1x is just C1 because the derivative of x is 1. Plus the derivative of C2x squared would be C2 times 2x. And we continue like this. The derivative of C3x cubed is C3 times 3x squared. The derivative of C4x to the 4 is C4 times 4x cubed. The derivative of C5x to the 5 is C5 times 5x to the 4. The derivative of C6x to the 6 is C6 times 6x to the 5. And that pattern would go on like that. Does everybody understand the differentiation that's going on here? Take your time. I actually need to use the bathroom, so take your time. All right. So we just differentiate one term at a time, just like you differentiate a polynomial. So the power comes down and you reduce the power by 1. X to the 4 becomes 4x cubed. You do that for all the terms. Now we plug in 0. So f primed of 0, well, this piece is 0. This piece is just C1. This would be C2 times 2 times 0 plus C3 times 3 times 0 squared plus C4 times 4 times 0 cubed plus C5 times 5 times 0 to the 4. All of those terms are 0. So what do we get? We get that f primed of 0 is C1. In other words, your first coefficient in the power series is equal to the first derivative of your function with 0 plugged in. That matches up with this, doesn't it? That's f1 of 0 over 1 factorial. The first derivative evaluated at the center divided by 1 factorial. And you can guess how we're going to continue these. We're just going to keep differentiating. I'll differentiate this thing as many times as we need to, plug in the center, and we'll verify that this formula really does hold. Next. F double primed of x. I need to differentiate f primed. This 0, this is gone. C1 will now differentiate to 0. C2 times 2x is going to differentiate to C2 times 2. C3 times 3x squared is going to differentiate to C3 times 3 times 2x. C4 times 4x cubed is going to differentiate to C4 times 4 times 3 times x squared. C5 times 5x to the 4 is going to differentiate to C5 times 5 times 4 times x cubed. C6 times 6x to the 5, look, just differentiate this piece. Forget about everything else. This is a constant. This is a constant. When you differentiate x to the 5, you get 5x to the 4. So this piece will differentiate to C6 times 6 times 5x to the 4. So I'm taking every term from this line, which is my first derivative, and differentiating it again. That's how we get the second derivative. The derivative of C1, it's a constant, is 0. The derivative of C2 times 2x, well, the x will differentiate to 1. So that's just going to be C2 times 2. The derivative of C3 times 3x squared, the C3 times 3 comes along. The derivative of x squared is 2x. I'm just doing that for every little piece here. And if you plug in 0, you'll get C2 times 2 plus a bunch of shit times 0, right? C3 times 3 times 2 times 0 plus C4 times 4 times 3 times 0 squared. All of these are 0. So f double primed of 0 is C2 times 2. I'm going to tuck these in our pocket as we go. Is everybody with me so far? All right, I'm going to do it again. I'm going to take this line and I'm going to differentiate it by differentiating each individual piece as though it is a polynomial. You can kind of start to see where this is going to go. Because if you differentiate x to the n times, you get n factorial. So this time the C2 times 2 is the constant. It's going to go away. C3 times 3 times 2 times x is going to differentiate to C3 times 3 times 2 plus C4 times 4 times 3 times x squared is going to differentiate to C4 times 4 times 3 times 2x plus C5 times 5 times 4 times x cubed is going to become C5 times 5 times 4 times 3 times x squared plus C6 is going to become C6, I've got 6 times 5 and then 4x cubed, x to the 4. And if you plug in x equals 0, then you get f triple prime of 0 is equal to C3 times 3 times 2. All the other terms are 0. So f triple prime of 0 is equal to C3 times 3 times 2. Now, this is why we have the notation, the f parentheses n, because after so many derivatives, I don't want to write 20 primes, right? Really, after the double prime, this notation becomes really inconvenient for higher order derivatives. So rather than writing f with 4 primes, I'm going to write f parentheses 4 for my next derivative. So f4 of x, the fourth derivative, this is a constant, it'll differentiate to 0. This piece is going to become c4 times 4 times 3 times 2 times the derivative of x is 1. Plus this piece is going to become c5 times 5 times 4 times 3 times 2x. The C6 piece is going to become C6 times 6 times 5 times 4 times 3x squared, and so on. Plugging in x equals 0, you see that f4 of 0 is C4 times 4 times 3 times 2 times 1 plus 0 plus 0 plus blah, blah, blah. So the fourth derivative of f evaluated at 0 really is c4 times 4 times 3 times 2 times 1. I left off the ones on these, but you can have a 1 here and a 1 here. So what's the pattern? Well, this is the same as saying C2 is equal to the second derivative evaluated at 0 divided by 2 factorial. This is the same as saying C3 is equal to the third derivative at 0 divided by 3 factorial. This is the same as saying C4 is equal to f4 of 0 divided by 4 factorial. So the pattern is precisely the one that we claimed it to be in the theorem. This pattern shows that Cn is the nth derivative evaluated at 0 over n factorial as claimed. That's the proof of the theorem. It's a beautiful thing. And at the heart of it is that if you differentiate x to the n times, you get n factorial. So if you differentiate Cn times x to the n times, you get n factorial times Cn. All the lower order terms will vanish because you'll have differentiated them to 0. And all the higher order terms go away when you plug in the center. We could have done this with a general Taylor series centered at A, and it would have worked out the same. It's just every time you take a little derivative there, you need to appeal to the chain rule. And so rather than doing a shitload of chain rules in each of these, I thought it would be simpler to look at the Maclaurin series case. But it's no harder, really. It just requires one extra step each time. All right, that's the proof of the theorem. How do we use the theorem? Well, you build a table. What this tells us is that finding a power series, so the lesson here, finding a power series is equivalent to finding a pattern in derivatives. If you can tell me what the nth derivative of a function is, then I can tell you a power series for that function. And conversely, if you can tell me a power series for that function centered at A, then I can tell you what the nth derivative for that function is evaluated at A. It's a beautiful thing. You can see now why e to the x is so friendly to this, because the pattern in the derivative for e to the x is totally trivial. E to the x is always its own derivative. So let me show you how this goes. Actually, let's take our break here. We're at a good spot to stop. I'll leave this previous page up. We're going to take about a 10-minute break. We're going to come back. What time? We're supposed to be 15 minutes, right? Yeah, okay. We'll come back at like, I hate to wait that long. Let's say 10 minutes. We'll come back at like 12 minutes, 1:05. Alrighty, lads and ladies, we are coming back. More power series stuff for you. So we have proven Taylor's theorem. Taylor's theorem, big brain idea. If you have a function that is infinitely differentiable, that is a function that you can differentiate as many times as you want, it never becomes not differentiable. Differentiating the zero is okay. Polynomials are infinitely differentiable. Then you can write it as a power series. And we have a formula for the coefficients of that power series. And we know that a power series is completely determined by its coefficients and center. So here's the way it goes. I give you a function, f, and a center, a, and then you have to compute these coefficients. Once you know these coefficients, you can plug them in here, and Bob's your power series. So let's do it. I said the easiest guy in the world to do this with is e to the x. I'm going to phrase it like this. Find the Maclaurin series f of x equals e to the x. Because series representations are unique, modulo the center. If you tell me the center, there's only one power series representation. So every function has one and only one Maclaurin series. You can't have two different ones because a Maclaurin series is centered at 0. And series are unique. Make a table. It's going to have a few columns. The far left column is n. The next column is fn of x. Next column is fn of a. And you can stop here if you want, but I like to also write the cn at the end. The two middle columns there need to be quite wide. Because you're going to be doing lots of differentiation inside of them. But for this guy, it's easy. So Maclaurin series, this means my center A is 0. So when I get to fn of a, what I'll be looking at is plugging in x equals 0. When n is 0, if I differentiate the function 0 times, I just get e to the x. And if you plug 0 into that, f of 0 is e to the 0, which is 1. And Cn, remember, is fn of a over n factorial. So this is going to be 1 over 0 factorial. When n is 1, the first derivative, f primed, is just e to the x. And when you plug in the center to f primed of 0 is still e to the 0, which is 1. Which means that this guy, which would be c1, is going to be 1 over 1 factorial. You can see where this is going. When n is 2, you're talking about f double primed of x, which is still e to the x. F double primed of 0 is still e to the 0, which is still 1. So c2 is 1 over 2 factorial. I think you would agree that if I differentiate n times, the nth derivative of e to the x is still e to the x, which means that the nth derivative evaluated at 0 is still going to be e to the 0, which is still going to be 1, which means that the nth coefficient is still going to be 1 over, n factorial. So Cn for f of x equals e to the x centered at a equals 0, Cn is just 1 over n factorial. Therefore, e to the x can be written as sigma n from 0 to infinity Cn, which is 1 over n factorial times x minus 0 to the n. But most people don't write x minus 0, they just write x. So sigma n from 0 to infinity, 1 over n factorial times x to the n. Some people write it as x to the n over n factorial, it doesn't matter. But I like to keep the coefficient a little separate so you can see which piece is which. Okay, of all the power series in the land, this one is the only one that's even close to as important as the geometric series. You could argue that geometric is more important or this is more important. They're both pretty badass, and these guys are kind of the most important ones. The downside of the Maclaurin series, like Taylor series table approach, is that at nowhere along the way do you get information about the IOC. So you got to do it fresh. You got to run the ratio test and test your endpoints. Now we've done the ratio test for this series before as an exercise, so I'm going to move quickly here. And then it ends up looking like this. And if you flop things around and cancel things out, this comes out to the absolute value of x times the limit as n goes to infinity of 1 over n plus 1, which is absolute value of x times 0. So L is less than 1 if and only if the absolute value of x times 0 is less than 1, which is true for any number, any real number x. Thus, the IOC here is negative infinity to infinity, all real numbers. And most of your problems, you're going to need to spend some time on your ratio test, right? It's not going to be this quick. But since we've done this one a few times before, I didn't feel compelled to go slowly through it. That means if you want to remember this, e to the u, and just like the other important power series, I wrote them with the variable u so that you can, plug shit in. This is 1 over n factorial times u to the n. And the convergence information here is all real numbers. It's good stuff. And if you need a power series for e to the x squared or e to the 5x or something like that, you can plug in x squared or 5x for u here, and it'll just plug in here, and you simplify that, and that gives you a new series. It's a big deal. Before I show you kind of the utility of this series, I want to just practice this process with a few other functions, right? Sine and cosine are the all-important ones, so let's do sine. And this is nicest for functions whose derivatives are super duper simple, right? That's the idea. If the derivatives get complicated, this gets complicated. Find the Maclaurin series where f of x equals sine x. Maclaurin series, so center is 0, right? There are problems out there where you want to center your series at some non-zero number, but most of the time we will work with series centered at 0. All right, so we make our table. And the nth derivative of f, the nth derivative of f evaluated at the center, and Cn, which is 1 over that thing factorial. And give yourself lots of space. Some of these are worse than others. Here, this one has a challenge to it. It's not as straightforward as the last one, but it's not bad. You always start with n equals 0. If I differentiate sine x 0 times, it stays sine x. If you plug 0 into that, you get the sine of 0, which I'm pretty sure is 0. So C0 is 0 over 0 factorial, which is 0. If I differentiate once, sine x will become cos x. And if I plug 0 into that, I get the cosine of 0, which is 1. So C1 is that 1 divided by 1 factorial, which is 1. If I plug in, if I go for n equals 2 now, I differentiate again, the derivative of cos x is negative sine x. And if I plug 0 into that, the negative sine of 0 is just 0. So C2 is that thing divided by 0, 0 divided by 2 factorial, that thing divided by 2 factorial, which is again 0. When n is equal to 3, the derivative of negative sine x is negative cos x. And if you plug 0 into that, you get negative cosine of 0, which is negative 1. So C3 here would be negative 1 over 3 factorial. When n is 4, the derivative of negative cos x, we're back to sine x. So this is going to be sine of 0. So C4 is going to be 0 again, right? Because sine of 0 is 0. This would be 0 over 4 factorial already, which is 0, 4 factorial. So I'm going to extend this table down a little bit. Like I said, these can be pretty space consuming. We're going to look for a pattern, but I want to see the pattern established a little better. When n is 5, we're back to cos x. Cos of 0 is 1. So C5 is positive 1 over 5 factorial. When n is 6, we're back to negative sine x. Negative sine of 0 is 0. So C6 is going to be 0 again. I'm not going to write the factorial. Oh, 1 notch. Okay. Okay. 0 over 6 factorial, which is 0. 7. The derivative of negative sine x is negative cos x. So that's the negative cos of 0, which is negative 1 again. So C7 is negative 1 over 7 factorial. Would anybody care to take a gander at C8? Somebody please take a gander at C8. Yeah, look at the patterns we've got established so far. Remember, it's all about patterns. Look just in the right-hand column. Yeah, very good. 0 over 8 factorial, which is 0, right? All the even guys, C0, C2, C4, C6. This is going to be 0. What about C9? Again, look at the pattern. 1 over 1 factorial, negative 1 over 3 factorial, positive 1 over 5 factorial, negative 1 over 7 factorial. Yeah, this is going to be positive 1 over 9 factorial. So this is one of those patterns that's hard to write down a formula for. If you want to see the formula, here it is. Cn is equal to 0 if n equals 2k is even. And it's equal to negative 1 to the k over 2k plus 1 factorial if n equals 2k plus 1 is odd. This is how you write that down. It's got to be piecewise and it's split along the parity of n. That doesn't really matter for what we're doing here. I would never ask you give me an explicit formula for these coefficients. I wanted the series. So if you can't see the pattern for Cn here nicely, what do? Write it out. Write out the series. That's going to be the game here. We're going to take these coefficients and we're going to use these coefficients to write out the first few terms of the series, hoping that we see the pattern. So what we've learned is that sine x is equal to 0 plus 1 over 1 factorial times x plus 0x squared minus 1 over 3 factorial times x cubed plus 0x to the 4 plus 1 over 5 factorial x to the 5 plus 0x to the 6 minus 1 over 7 factorial x to the 7 plus 0x to the 8 plus 1 over 9 factorial x to the 9, and so on. Now, if I skip writing the zeros, this looks a shitload nicer. That's the big deal. Just skip this, get rid of, don't write the zeros, which is like the natural thing to do. This becomes 1 over 1 factorial times x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the 5 minus 1 over 7 factorial x to the 7 plus 1 over 9 factorial x to the 9, and so on. What does this remind you of? What other power series looks a lot like this? Imagine, yeah, go ahead.
Sorry, continue.
I was say, imagine the factorials aren't there. What power series would this be without the factorials?
The alternating harmonic series?
But just the odd parts and with x's. It's arctan. This, if you took away the factorials, this would be the same as the series for arctan of x. And in other words, in sigma notation here, we can rewrite this as sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. It's identical to the arctangent series. It just has the 2n plus 1 factorial rather than regular 2n plus 1. Strange connections between these seemingly unrelated functions. It's really, really pretty amazing stuff. And you can learn way more badass shit using power series than you would ever believe. But let's record the result. Write it down somewhere nice. I'll write it as sine of u sorry, u to the 2n plus 1. And the IOC here, I'll let you do it, is again negative infinity to infinity. You run the ratio test. You gotta do the ratio test here to get this. But that's your next must remember forever and ever, amen, power series. You've got that, and e to the u, right? That was the other one that we figured out. He also has IOC, negative infinity to infinity. There's a word for functions like this, whose power series interval of convergence is the whole real line. They're called entire functions. All right, I've got one more badass power series that I need to show you here. You can probably guess what it is. It's cosine, right? Cosex. Now we could go back through that whole process to get cosex. Should we do that, or is there a smarter way to get a series for cosex from what we have on the screen?
Do we take a derivative of the sine power series?
Yes, very good. If I differentiate this, sine becomes cosine, right? So we know, I guess I should write here, example, find the power series for fx equals cos x. And we know that sine x has series sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. And that cos x is equal to the derivative of sine x. Those two facts will do the job. So sine x, cos x is equal to ddx of sine x, which is ddx of sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. There's one thing you need to be careful about here. Who remembers the subtle thing that can happen when you differentiate a power series? One subtle point from Tuesday's lecture. What was it? What can happen?
Its integral of convergence can change.
Well, you could lose an endpoint. That's true, right? But there was something that made the integration and differentiation different. There was a step that was involved with the differentiation that we didn't have for the integration. Does anybody remember that?
Is n equals 0? Is that
Right. If the
Sure.
series you're differentiating has a constant term, then the starting index will change, like Josh and Matthew are saying. So I'd say up here, recall, if f of x equals sigma n from 0 to infinity cn x minus a to the n has a non-zero constant term, then f primed of x will be sigma n from 1 to infinity. LCM n x minus a to the n minus 1. Emphasis on this part. So if it has a non-zero constant term, then we bump the starting index, but only then. Does this series have a non-zero constant term? What's the very first term of this series? Yeah, so the constant term here is 0. I think maybe if you're unsure about this, the thing to do is to write out the series. So the first term of the series, when you write it out like this, is x. It's -1 to the 0 over 1 factorial times x to the 1, and then minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7, and so on. So this does not have a constant term. All right, or if you want to think of it the other way, the constant term is equal to 0. So the derivative of this guy, the derivative of this guy is 1 minus 1 over 3 factorial times 3x squared plus 1 over 5 factorial times 5x to the 4 minus 1 over 7 factorial times 7x to the 6 plus and so on. Or you could do it all in sigma notation. All right, you could differentiate staying in the sigma notation. This would just become 2n plus 1 times x to the 2n. This is what it looks like right now. And there's simplification here. 1 minus, what's 1 over 3 factorial times 3? What's n over n factorial?
Factorial.
So if you take 3 factorial and divide it by 3, you get 2 factorial. You take 5 factorial and divide it by 5, you get 4 factorial. So this is 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6, and so on. Think about it. 5 factorial is 5 times 4 times 3 times 2 times 1. So when you divide, when you cancel one of those 5s, you're left with 4 times 3 times 2 times 1. So what is this? I can go back to sigma notation now. This is sigma n from 0 to infinity, alternating again, -1 to the n. Downstairs here, instead of 2n plus 1 factorials, I have odd, instead of odd factorials, I have even factorials. 0 factorial, 2 factorial, 4 factorial, 6 factorial. So this is 2n factorial. And then x to the 2n, even powers of x. Yeah, we do need the factorial, and we'd want to put 2n in parentheses if we're being careful typing it. But yeah, that's, you get the idea. This could be done in sigma notation. Again, if you wanted to see what this looked like in sigma notation without writing it out, the next step here would look like sigma n from 0 to infinity. I don't bump the starting index because this doesn't have a constant term, over 2n plus 1 factorial times 2n plus 1 times x to the 2n. I just follow the differentiation rules. Bring the power down, decrease the power by 1. And then the same cancellation thing here is true. If you cancel the 2n plus 1 and the 2n plus 1 factorial, you get -1 to the n over 2n factorial x to the 2n. It's slightly faster like that. We got to a good question in the chat there. What about power series for tangent? We got sine, we got cosine, we got e to the x, log x, arctangent. You could get a power series for tangent by dividing the power series for sine by the power series for cosine. But dividing and multiplying power series is actually really hard. Like really hard. Think about how you multiply polynomials, right? You have to FOIL everything out. Think about dividing polynomials. Remember that from pre-calc, like synthetic division? That was just division by one term. If you want to divide a big polynomial by another big polynomial, you got to do polynomial long division. Imagine both of those polynomials are infinitely long. Now we've got a real challenge. So you could get a power series for tangent by dividing the series for sine by the series for cosine. But the truth is, I don't remember the power series for tangent off the top of my head, and I think it's probably quite complicated. It would necessarily have to have a fairly small interval of convergence if we wanted to center it at 0, because tangent is not infinitely differentiable, right? There are places where the tangent function is undefined, discontinuous. So we run into some problems looking for a power series for tangent. But as long as you stay close to 0, I'm sure one exists. I just don't know it off the top of my head. You get it by dividing the series for sine by the series for cosine, but again, that's hard. So there are some other series I'd like to show you before we move on. But there's series that we can get by playing with the series we have. Now you got me curious. I can't, I'm sorry. Bernoulli numbers. Yeah, this one's a little complicated. The patterns here are not super obvious. Yeah, power series for cotangent is actually a little nicer. I've seen that done a few ways. This would be a good idea, yeah. All right, but we don't have time for that. So power series for tangent a little bit weird. Let's see. I'm not going to make you guys worry about Taylor's inequality. We discovered these series. X cos x, sure, we can do a little bit of that. I'm not going to kill you with that. Wicked. So yeah, here's on page 768, there's a super important table of series you guys need to know. These are all of them. The bottom one, I'm not even going to hold you to. It's Newton's binomial theorem. It's a binomial theorem that works for non-integer powers. I think better than memorizing this is building the table for it as you need it, because you guys will have trouble defining the binomial coefficients, these numbers that you may or may not remember from pre-calculus, when k is not an integer. But you need to know all except the last line of this. And in addition to the radius of convergence, I mean, you know the center, you need to know the IO, so you need to know what goes on at endpoints. So yeah, let's look at some problems. Again, that's on 768. Yeah, let's do that one. I forgot, we haven't done that yet. Anybody know why the integral of e to the negative x squared is important? Has anybody ever taken a statistics class?
Way too long ago.
So this thing called the normal distribution.
Oh.
This is how a lot of statistics in nature are distributed. You may have heard of that book called The Bell Curve, which is like horribly insulting to most people who like don't want to study those particular things. But they say IQ is distributed along a bell curve. That's that book. It's horrible. But lots of things are height. If you look at like a million and one different statistics, you come up with a random statistic from nature, odds are it's distributed normally. where the kind of mean, the average is in the middle. And then as you walk further away, when you talk about like in particle physics, they found the Higgs boson with like 5 sigma certainty. They're talking about standard deviations, like how far outside from the average of those measurements this would have to be in order to be wrong. Hugely important thing from statistics, immeasurably important function, and particularly finding the area underneath it. Like if I wanted to say this was describing height, right? So maybe the maximum height of a person is 10 feet tall or some shit. Or no, we need to go the mean, right? Not the max, the mean. So say the average height of a person is, whatever, we'll be generous, 6 feet tall. Then the probability that a randomly selected person would be over 6 feet tall would be the area under this curve to the right of 6. That's the vibe here, or something like that. Oh, no, sorry, I'm scaling vertically, aren't I? Yeah, no, to move the mean, we'd have to scale horizontally. So I could do it like this. I don't want to burn too much time on this. Let's say 5.5. That's probably more realistic. So the probability that a randomly selected individual, if the average height is 5.5 feet, the probability that someone is greater than 5.5 feet tall would be the area under this curve to the right of 5.5. So let me graph that 0 less than y less than x, where x is greater than 5.5. Which is exactly half. So the integral of this thing is 1 when you normalize it appropriately, and this would be exactly half of that area. The probability that you're over 6 feet tall would be this area, right? And so on. That's how this stuff works in statistics. It's awesome. But it all revolves around areas under this curve. So we need to know how to integrate this curve. This is not something you can do normally. This function doesn't have a closed form antiderivative. It's not an elementary integral, but now we can do it. So we recall that e to the u is sigma n from 0 to infinity, 1 over n factorial times u to the n, which means e to the negative x squared, you just got to plug in negative x squared for u, is sigma n from 0 to infinity, 1 over n factorial, negative x squared to the n. And we need to simplify this before we can do any special stuff like integrating and differentiating. That's sigma n from 0 to infinity, 1 over n factorial times negative 1 to the n times x squared to the n, which is sigma n from 0 to infinity, 1 over n factorial, negative 1 to the n, x to the 2n. And the IOC at the start is all real numbers, so we can trust that this is also going to be all real numbers. Therefore, the integral of e to the negative x squared dx is equal to the integral of that series, sigma n from 0 to infinity. I'm going to put these together as negative 1 to the n over n factorial, and then x to the 2n dx. Which is c plus sigma n from 0 to infinity, negative 1 to the n over n factorial times 1 over 2n plus 1 x to the 2n plus 1. That's the antiderivative of what's called the error function. That's the name for this ERF. The Gaussian error function, Gaussian distribution or normal distribution, there's a bunch of terms. All right. So again, it's a lot like the stuff at the end of 11.9. It's just that we've got more doors open to us now because we have this Taylor's theorem for coming up with series for other functions. One of the things that you need to get good at is recognizing whether you should start from scratch or use one of the known series. Right here, I could use one of my known series to start finding a series for this. One of the basic things you need to recognize in this section. But there are other problems where you just need to cook up a power series. I'm going to do, well, no, we came back a little bit late, right? Let me take the last 10 minutes here. Oh, it's hour 15, right? Yeah, we're good, we're good. Take a few more minutes here and show you one more challenging problem with that table. So those can get tricky. And I'd like to do a problem where we're not centering the series at 0. Here's what we're going to do. We're going to find power series of f of x equals the square root of x centered at a equals 1. So this is not a Maclaurin series, right? The center is somewhere else. It is a Taylor series, and I'm going to use Taylor's theorem to do it. Meaning I'm going to build that table. Here I'm going to give myself some space because these derivatives will get a little bit complicated. Fn of a here is Fn of 1. Cn. Remember those odd factorial-like products? The reason I had to show you those earlier is in preparation for this problem. It will show up here. All right, are we ready? If I differentiate 0 times, then I just have my function, which is the square root of x, or x to the 1/2. And if I plug 1 into that, I get 1 to the 1/2, which is 1. So C0 is 1. If I differentiate 1 time, then I'll get 1/2 x to the negative 1/2. And if I plug 1 into that, then I get 1/2 times 1 to the negative 1/2. That's just 1/2. So C1 is 1/2 divided by 1 factorial. If I differentiate twice, then I'll have 1/2 times negative 1/2 times x to the negative 3/2. And if we plug in 1 for x there, that becomes 1/2 negative 1/2 1 to the negative 3/2. Now 1 to the negative 3/2 is still 1. That's 1 over the square root of 1 cubed. But 1 raised to any power is always going to be 1. I'm not really worried about this piece. It's more of these pieces we need to keep track of. So this is negative 1 over 2 squared. So C2 is negative 1 divided by 2 squared all over 2 factorial. If I go again, I'll have 1/2 times negative 1/2 times negative 3/2 times x to the negative 5/2 as my third derivative. Plugging in 1 here, we got 1/2 times negative 1/2 times negative 3/2 1 to the negative 5/2 power. So C3, I'm going to need some more space here. This is, I've got negative 1 times negative 1 is negative 1 squared. That's divided up times 3 times 2 to the 1, 2, 3. Sorry, divided by 2 cubed. And then I also have to divide by n factorial. So I'll put a divided by 3 factorial here. That's weird. When n is 4, this will be 1/2 times -1/2 times -3/2 times -5/2 times x to the -7/2. That's the fourth derivative of that. Plugging in 1 for x, this is 1/2 times -1/2 times -3/2 times -5/2 times 1, 7/2. So C4, how many powers of -1? I've got 1, 2, 3. Cubed. And then my numerator, I've got 3 times 5. My denominator, I've got 2 to the 1, 2, 3, 4. And then from the Cn, I have a 1/4 factorial. So the question is, can you recognize the pattern? Let me help. Let's come back to C2. Now this is really 1 times 3. This is really 1 times 3 times 5. So up here I can think of this as -1 to the 1 times 1 over 2 to the 2 times 2 factorial. Just cleaning up the fraction a little bit. The previous guy I can think of as -1 to the 0 over 2 to the 1 times 1 factorial. So now if we look at those, we'll see a pattern, right? -1 to the 0, -1 to the 1, -1 to the 2, -1 to the 3. The odd product upstairs is weird. You got nothing, then 1, then 1 times 3, then 1 times 3 times 5. Okay, that's weird. Downstairs here, you've got 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So if we were to guess at C5, -1 to the 0, 1, 2, 3 should have a -1 to the 4. The product upstairs is 1, 1, 3, 1, 3, 5. And you see if you were to differentiate this again, you would get a 7 from the 7/2. So this is going to be 1 times 3 times 5 times 7. Downstairs here, you've got 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So this should have a 2 to the 5. And then, of course, the 5 factorial from the formula. C6 would be -1 to the 5, 1 times 3 times 5 times 7 times 9 times 2 to the 6 times 6, divided by 2 to the 6 times 6 factorial. So eventually we do see the pattern. It's just a little bit weird. The pattern shows us that Cn is -1 to the n minus 1. Right, the power of -1 is 1 less. Times this odd product, 1 times 3 times 5 times 7 up to 2n minus 1. Sorry, 2n minus 3 maybe. Yeah, 2n minus 3. And then downstairs, 2 to the m times n factorial. That's it. There's one teensy weensy little catch, and that's that it doesn't work if you plug in 0. So this is for n greater than or equal to 1. So f of x, my square root of x, should be equal to sigma n from 0 to infinity Cn times, remember my center here is 1, x minus 1 to the n, where Cn is this thing. But this thing only works if n is greater than or equal to 1. So you got to pull out the n equals 0 term. That's C0 plus sigma n from 1 to infinity Cn x minus 1 to the n. And now the series is just showing the indices that we're happy with. So I can use this formula. C0, I know what C0 is. I actually calculated it. Up here, remember, it's 1. So this is 1 plus sigma n from 1 to infinity, -1 to the n minus 1 times 1 times 3 times 5 up to 2n minus 3. You could also call this 2n minus 3 double factorial if you know that notation, divided by 2 to the n times n factorial, all times x minus 1 to the n. This is a challenging problem of this nature. All right, the first few ones were easy. This one is not. Something like this is on the upper level of exam difficulty. I have given a problem like this on a test before. I think probably this semester I wouldn't do that, but be aware, right? This is within that territory. It's not totally out there. Ignore it. It's just too hard. It's within exam range. Or maybe I just ask you for the first 5 terms instead of the whole series, so you don't ever have to write this whole thing down. You can just calculate a few of these. Something like that, I could certainly put on the test. Okay. I think that's probably about your limit of patience for this stuff. I imagine you guys are feeling a little bit burned out. So I don't want to push too much further, but I do need to conduct that poll. So let me structure the poll here. I'm going to turn off my screen share. Actually, let me, sorry, cancel it. I'll leave it up for now because people are still writing. But let me create the questions. Oh, I can't do this while you watch. While you're able to look at the notes. Oh, that's okay. Some type of question. All right, so your first option here is exam 2 will be in person next Thursday, covering all the material. So power series and polar curves and parametric equations. That's one that would involve me creating an extra lecture over the weekend that you guys could watch at your own time. Then we would have another lecture on Tuesday, and then the exam would be in class on Thursday. We could do it during the lab hour. That way we could review during the first part of Thursday and have the exam during the lab hour. The next option is exam 3 will be Thursday 4/22 in class, covering only power series. And then the last option here would be exam 3 will be take home. Alrighty. Are there any questions about what these 3 options mean or would do for us? All right, I'm gonna go ahead and launch the poll. Everybody please answer. Could still go either way. Okay, I think with that balance, 9 out of 13. Oh, let's see, interesting.
Professor, I recommend a you take the two runner-ups and we vote on those two. Because remove the option that has the lowest amount of people and then do another poll with the two highest.
Sure.
Yeah, because this is going to be close. I know it is.
Yeah, we're still waiting on a few other people here. If we were to sum the two options 1 and 2, we still don't have enough to beat option 3 at this point right now, but we are still waiting on some other folks to vote. So if you've wandered off or something, please come back and vote now on how you would like exam 3 to take place. We do need this settled today. Oh, is it the case that, let me see. Okay, I think everybody probably has voted now. It's just myself who's not being counted, right? Yeah, okay. All right. So the in-class covering only power series was the lowest selected. So we can run this one more time with just options 1 and 3. I will end. It's going to let me highlight. It's not. All right. So we're going to close this, create a fresh poll, clear existing results. All right. Oh, no, sorry. Can I get rid of this? Edit. There we go. All right. Okay. So again, how do we want exam 3 to take place? We could do in class Thursday 4/22, covering all material. Or take home test. Let's do the start of the final. Alrighty, we're gonna launch this one more again. It's kind of like a STV thing that works fine. So launch, no, okay, relaunch. I've ever launched 2 polls. It's not letting me. Oh no, here it is. Here's the poll. Okay, there we go. All right, launch. Let's see, I'll be right back. Okay. Yeah, and it looks like we have everybody in now, and the take home still has it. So it'll be the take home test. I will give it out to you guys on Thursday after class. So next week will just be like regular lecture. And then at the end of class on Thursday, I will send you guys a PDF that you'll need to print, sign your honor pledge, complete, scan, and upload. It'll be due on the day of the final. Due at the start of the final, so like before we begin, on which again for you guys is the 27th at 1 p.m. Alrighty, so we've got a plan. Hope you guys have a good rest of your day. Please work hard on that homework. And if there are any questions, yeah, Cody.
Yeah, will you have an office hour tomorrow or today?
So I had an office hour earlier today, and I have another one tomorrow at 1 p.m.
Perfect, thank you.
Yep. Take care.
Have a great day, Professor. See you later.